We have previously practiced the two-dimensional single-speed steady-state neutron diffusion equation in rectangular geometry. Now we will move to the two-energy group neutron diffusion equation solving. We will solve this equation in block reactor first. Then later we will solve this equation in multi-assembly real reactor. So the previous one group problem, we only considered the spatial discretization. So we only have the meshes in the space. However, to precisely model the neutron behavior, the neutron energy must be discretized as well. So we know that the neutron will have a different energy. We have to consider this energy distribution and how the neutron will migrate from one energy group, from one energy to another energy, in order to increase the accuracy of our result. Therefore, we are going to split the neutron energy into different groups. Okay, we call it energy group. So the energy groups are labeled as group 1, group 2, until group G. So the capital G represent the total number of energy groups. For neutron diffusion modeling, normally the G is at least 2, so 1 is not enough for sure. For 2 energy group, in sometimes it will be enough. For example, for modeling the light water reactor, 2 energy group will give you acceptable result. And if you want to have a more accurate result, you can increase this energy group, but it's usually lower than 10. Okay, so it means that the energy group is not a very big number like the meshes. In our course, we will only solve the 2 energy group problems because this PDE modeler, this graphic user interface, can only solve a system of 2 coupled differential equations. So this is a limitation of this PDE modeler. However, the MATLAB PDE Toolbox is able to solve more energy groups, but you have to use the programmatic workflow. Means that we need to move to the pure script workflow. That is not covered by this course. So again, in this course, we will just solve 2 energy groups problem using this PDE modeler with graphic user interface. So we use the group G to represent the energy group. Then group 1 is the highest neutron energy. In order to couple those equations, we are going to introduce 2 additional variables. These 2 variables are considered as the material property. The first one is the scattering cross-section. So this one is the probability for the neutron to scatter inside this material. So the neutron may hit the atomic nucleus, then it is bounced to another direction. So we have this sigma s represents scattering. And we will also have another subscript. In this case, we have 1-2. It means that after this scattering, the neutron energy will be changed from group 1 to group 2. It means that the neutron energy at the beginning it is high, so it is in the energy group 1. After this scattering, the neutron loses energy, then the energy will be classified into the energy group 2. So this is the meaning. So this one is called the down scattering. The neutron, after this scattering, the neutron energy is reduced. So this is the possibility of energy group 1 neutron becoming energy group 2 neutron through this scattering collision. The neutron diffusion equation does not use the self-scattering like sigma s G to G. It means that after this scattering, the neutron is still inside the same energy group. Therefore, the sigma s G to G are set to 0. And also, if there are only two energy groups, in our case, we only have two energy groups, then the upscattering, for example, sigma s 2 to 1, neutron energy is increased from group 2 to group 1 after this scattering. We consider this cross-section is also 0, because it would be nearly impossible for the neutron to gain enough energy to jump from energy group 2 to energy group 1. So sigma s 2 to 1 is 0. So this is our assumption. In addition, we also have the fission spectrum chi. It looks like X, but it's Roman letter chi. So this chi represents the fraction of newly born neutrons in each energy group. It means that the neutrons are generated after each fission, and those newly generated neutrons have different energy. Some of those neutrons are in energy group 1, some of the neutrons may in energy group 2. So this chi represents the fraction of the newly born neutrons in each energy group. If we say that chi 1 is equal to, for example, 0.99, it means that 99% of the newly generated neutrons are in energy group 1. Again, if there are only two energy groups, we are going to say that the chi 1 will be equal to 1 and chi 2 is equal to 0, because that all the neutrons newly generated from the fission, they have very high energy. So most of the case, they are in the energy group 1. Therefore, to simplify our equation, we are going to say that the chi 1 is equal to 1 and chi 2 is equal to 0. This is also our assumption, and will also yield very good result. Next, let's introduce the two-group neutron diffusion equation. So here we have this two-group neutron diffusion equation in two-dimensional geometry. And you can see that for both cross-section and also the neutron flux, they will have a subscript. The subscript 1 represents the group 1 cross-section or group 1 neutron flux, and subscript 2 represents the group 2 property. So at this moment, we will have this, after solving these equations, we will have the neutron flux on each node, and on each node we will have two values. One is the value for phi 1, another is the value for the phi 2. Okay, so on each node we will now have two neutron flux. By observing this equation, you will see that there are a couple differences compared to our single speed or one group neutron flux, neutron diffusion equation. The first one is this absorption or loss term. We now will have the scattering. So the neutrons may be absorbed by this absorption cross-section, may also be scattered by this scattering cross-section. It means that if this neutron undergoes scattering reaction and it goes to the group 2, then this neutron is no longer group 1 neutron. So we are going to remove this neutron from the group 1 equation. On the right hand side, we'll have this fission. So for this fission, we have the mu sigma f1 phi 1. So this is the fission caused by group 1 neutrons. And we also have the fission caused by group 2 neutrons. Okay, we will do them together, sum them together. On the right hand side, we also have another scattering term. So we may also acquire, for this energy group, we may also acquire some neutrons from other energy group. For example, for this case, we have upscattering. So the group 2 neutron undergoes scattering, then it becomes the group 1 neutron. Okay. So those will be the additional terms for the 2-energy group. Then, as mentioned in our previous slide, we can assume that there is no upscattering. Means that sigma scattering from 2 to 1 will be 0. In that case, we are going to remove this term. We also assume that all fission neutrons are in group 1, so that we have chi1 equal to 1 and chi2 equal to 0. So if chi2 is 0, we have entirely this one to be 0. Okay, this one is also 0. Okay, then chi1 is just 1. Therefore, we can simplify this equation to this red equation. And by this simplification, we are eliminating a couple terms. Okay. Then we also compare this MATLAB equation. Okay. In MATLAB, the equation for a general eigenvalue system is shown by this formula: negative inverse triangle C inverse triangle U plus AU is equal to lambda du. This equation actually is represented in matrix form. So C, A, and D, they are all matrix, and U is a vector. Then lambda is a scalar value. We just compare these two equations. Okay, these two sets of equations. We will be able to know that the C is equal to D1 as C11 and D2 as C22, and the C12 is 0, C21 is 0. Okay. Because this one is your C11, this one is your C22. Okay. Then the A is determined by this formula. Okay, A is determined by this formula. You can see that A11 is equal to CA1 plus CS122, and A21 is negative sigma S122, and A22 is sigma A2. For the D is for the fission. Okay, and we only have the non-zero value for D11, D12. They are mu sigma F1 and mu sigma F2, and D21 and D22 are both 0. For the K, it is still equal to 1 over lambda, or lambda is equal to 1 over K. And we are still trying to find the smallest lambda. Because the equation now is two-dimensional, or you have two equations. So our boundary condition also become two rows. Okay, two rows, two columns, or two rows for a vector. They are listed here, and we will go over those values using some examples. For example, for direct light, the H is a matrix, so it is a diagonal matrix, so just 1, 1, and R is all 0. For the Newman, vector boundary condition is Newman, and G is all 0, and Q is equal to 0.46922 times an I matrix. Then for the mirror is all 0. For the albedo boundary condition is also Newman, and the only difference is that this Q is alpha. Alpha will be given as the albedo factor given by the problem. Next, we will use one example to show where to enter those values into the PDE Toolbox. So this one comes from the Stacy's textbook. Okay. This one requires the student to write a computer code to solve numerically for the fast and thermal flux distribution and the effective multiplication constant in a two-dimensional cut through a very tall reactor core. Fortunately, we have the MATLAB, so we don't have to worry about how this equation is solved internally. We just need to learn how to describe this model using the MATLAB PDE Toolbox. In addition, this one is a very tall reactor core, and so the z direction is infinite, so it will be a two-dimensional problem. So the reactor core extends from -50 to 50 centimeter for the x. Region 1 of the core extends from 15 centimeter to 55 centimeter along the y direction, and region 2 is from 55 centimeter to until 105 centimeter. This is for the y. The core is then entirely surrounded by a 15 centimeter thick reflector. The two group constants for the core and reflector are given in this table. So you have 3 regions with 3 different materials: core 1, core 2, and also the reflector. And it is two group problem, so you will have the group constant for group 1 and also group 2. So we have the chi is 1 and 0, so this will meet our assumption. And now the previous derivation will be used. You also have the mu sigma f, sigma a, sigma s, 1, 2, 2, and d. Okay. So how to draw this core configuration is the student's responsibility. Okay. For demonstration purpose, I'm going to show this figure here. Okay, and we know that this core is from -50 to 50 along x direction. Then for the y is core 1 stacked with core 2. Then you have a reflector surrounding this entire geometry. Okay, you will see that this core is symmetric along the center line. Therefore, we will model either the left half or the right half in order to save the computing time. Okay. If we model one half of this core, then along this symmetric axis, we are going to apply the reflective boundary condition. All others will be vacuum. Now we will move to the MATLAB to demonstrate how to solve this problem. My MATLAB opened. First, I'm going to launch the PDE tool. Okay. And I'm going to turn on the grid and start the drawing. So I'm going to draw the core 1 first. So I'm going to construct the right half of the core and draw the core 1. Okay. For core 1, change it to core 1. X will be 0. Until y will be 15. The width is 50. The height is 40. Okay. Now we added this access limit. For example, from -10 to 70. Then from -10 to 130. We draw the core 2. It is core 2. And left is 0. Then bottom will be 15 plus 40, that is 55. Width 50, height 50. Click OK. We will turn on the axis equal. Next, I'm going to draw the reflector. The reflector will be 0 and 0. Then 15 centimeter thick. So this one is 65. Top is 120. Click OK. And we change this one to generic systems. Okay, generic system. So that you have 2 equations. Then we save this file. I'm going to save this one as Neutron Diffusion Example 2. And for the model. Next, we will move to the PDE coefficient. Go to the PDE mode. Okay. And show subdomain label. So we have 3 regions. And here, I'd like to mention that there's a known bug, okay, that will prevent you from continue this definition. For example, I'm going to show that here is core 1, okay, our core 1, and we double-click this one. It will bring up this PDE specification. In this PDE specification, we need to choose the eigen mode. Okay, to our right, to our left, it is eigen mode. We need to enter the C1, C11, and C12. Based on our formula, we know that C11 is D1. So we need to enter 1.267. And we need to enter this C22 as the D2, which is 0.354. But if you click OK, there will be an error saying that subdomain must have a constant C matrix. Okay, you may not understand what it is saying. Okay, so the problem here is that the MATLAB use different internal representation method to represent a different type of the C matrix. For example, here you have C11 not equal to C22. Okay. However, by default, C11 is equal to C22. It means that MATLAB will use different internal storage method to store this different C. Okay. It means that if all other cores, all other regions using the C11 is equal to C22 storage method, you cannot change this one to a different method that will determine the C11 is not equal to C22. Therefore, to overcome this error, let's first click OK and click cancel. To overcome this error, we have to change all the regions to use a method that can store a C matrix with C11 not equal to C22. So in short, we are going to click Control A. In Mac, that's Command A. In Windows, that's Control A. Okay. Click Command A or Control A. Then we can select everything. Okay, we just select everything. Then we double click a region. Okay, we double click a region. Then you see that by default, C11 is equal to C22. Okay, we are going to change everything together. Okay, change everything together. We change the C11, for example, to 2. Okay, we just randomly change the C11 to be a different number with C22 and click OK. Now it will accept your input. Okay. Now we left click anywhere outside this geometry to deselect everything. Then we double click the core 1. Okay, double click core 1 and enter our value normally. So we have we have C11 that is D1 1.267. C22 that is our C22 is our D2 354. Okay, and A11 is sigma A1. Sigma A1 is 0.0121. Okay, sigma A1 plus sigma S122. Sigma S122 is 0.0241. Okay. It will accept a formula, so we leave it like this. So you don't have to calculate what is the result. Then A12 is always 0. A21 is negative sigma S122. So negative 0.0241. And A22 is sigma A2, which is 0.121. And for the D, remember that the D21 and D22, they are both 0. And the D11 is mu sigma F1, 0.0085. And the D12 is mu sigma F2, 0.1851. Okay. Then we double check this matrix to see if there's any error. Okay, click OK. Make sure you choose the eigen mode. Click OK. Then we repeat this process for the core 2. For the core 2, sigma 11 is D1 for core 2, 1.28. This one is D2 for core 2, 0.4. A11, that is sigma A1, 0.01, plus sigma S122, 0.016. Here, negative sigma S122, negative 0.016. A22 is sigma A2, which is 0.1. Again, remember to set this one to 0. And the D11 is mu sigma F1, 0.006. And this one is D12 is mu sigma F2, 0.15. Okay. Then double check to see if everything is entered correctly. Pay attention that if the number is misplaced or you have a wrong number entered into this dialog, it may cause your system solving to diverge. So if you do not have your result quickly, and most likely you have the wrong physics. Last one is the reflector. For reflector, again, we follow the same procedure. So that is 1.13 and 0.166. Then A11, that is sigma A1, 0.0004 plus sigma S, 0.0493, negative 0.0493. Then this one is sigma A2, 0.02. This is 0. And the reflector is not filled, so we do not have the efficient cross-section. Now we double check to see if everything is entered correctly. Okay, click OK. Now we save it. Next, we are going to set our boundary condition. So click this button. Now we go to the boundary mode. First, we set the vacuum boundary condition. So hold your Shift key to select all the external boundaries. So top, right, and bottom. Double click. We know that for vacuum boundary condition, it is Newman. So we click Newman. Now you see that the G is a vector and the Q is a matrix. Okay. So the G are all 0. And the Q will be, Q11 will be 0.46922. 46922 for Q22. Okay. This is for the vacuum boundary condition. Click OK, it will become blue. Okay. Next, we set these boundaries to be mirror or reflective. We select all the left boundaries, change it to Newman. For mirror boundary condition, the G is a 0 vector and the Q is a 0 matrix. So we click OK. Okay, click OK. Next, we go to the mesh. Okay, go to the mesh. So we click this button to change to the mesh mode. So apparently the default one is too coarse. So we select the mesh parameters. Okay, and we enter some value. So this one you have a 65. So we enter, for example, enter 5. Click again. Okay, you get a denser mesh. You can further reduce that if you think it's not enough. In this case, I'm going to use 1. Okay. Okay, now it looks better. So you have a relatively fine mesh. Next, do not click solve before changing this parameter. Okay, and if you do that, most likely your calculation will be forever. Okay. Okay, change the solve parameter. We change this one to be from 0 to 2. Okay. Click OK. Then we can solve it. Okay. So we found 13 eigenvalues. If we change this one to from 0 to 1, we can try that and click OK and solve it. Still, we will have our result. Okay, either way is fine. Here, I'm going to just try for the 0 to 2, because for 0 to 2, somehow the result will be not the same here. Okay, previously it was all negative. So we click this one and change this one to hot, to jet. Okay, and plot. All right, then it looks better. So for my result, you see that everything is positive. Okay, everything is positive. Therefore, we do not need to change this plotting command here. If your result is all negative, then again you need to change this one to user entry and put the negative u here. Okay. We can also have the height. Okay, check the height. Click plot. Then we will have this figure. This figure is flux 1 profile. Okay, you see that it is u. Okay, it is u. We can also have change this one to v. Okay, change this one to v. Then click plot again. Now here you will see that this one is okay. We need to change this one to v as well. Change both the color to v and the height to v. From this one, you will see that it is group 2 flux profile. And the K will be equal to, I'm going to move this one away. Okay. So the K will be equal to 1 over lambda. Okay, 1 over lambda. That is 0.87549. Okay. So the K will be 1.1422 for this problem. For this problem, it only asks us to calculate the K and also the flux profile. And we have solved this problem. And this will conclude this calculation. Now we will go back to the, so this is your U, so this is the V. Okay. One is the top view, another one is 3D view. And next, we are going to go back to our slides to review what we have done for this two-dimensional two-group. Now let's go back to the slides and review what we have practiced. So after you have constructed the core geometry, you need to enter the PDE coefficient. The first thing you need to remember is that there is a bug, and this is caused by different storage method used in MATLAB to store its C. Okay. So MATLAB try to use a vector of different lengths to store this matrix C. Okay, if your system is very large, if you have, for example, many differential equations coupled together, then the C matrix is very big. And the MATLAB will try to use some simple method to store it. One format is that the C has C11 equal to C22. Okay, C1 equal to C22, and others are 0. This one is considered is called scalar C. Okay, it uses the shortest format to store this one. And however, in our case, most of our case, the C11 is not equal to C22. Okay, you see that the C1 and also C2 are different values. So this one is called, in MATLAB, is called a two-element column vector C. Okay, and certainly if C12, C21 are not 0, you have a more complicated format of the C matrix. Okay. So by default, the C matrix of all the subdomains are of the first type. So by default, C11 is equal to C22. Okay. And the MATLAB internally uses the scalar C storage method. However, we need to use the second type. Okay, second type. If you try to change the C matrix to the second type in one subdomain, while our other subdomain has the C matrix of the first type, this is not allowed. The MATLAB will give you an error because different C format cannot coexist in the same problem. Okay. In that case, we will have to change all the subdomains together. So the workaround is that in the PDE mode, you press Ctrl A, okay, in order to select all the subdomains. Then you double click any selected subdomains to change this PDE coefficient for all subdomains together. Okay, we just simply change the C11 to be a different value from C22. Then our subdomain C matrix will be changed to the second type. Then you can change those subdomains one by one at a later time. This will not give you any additional errors. So this is very important. You need to pay attention. You have to do this for each of your problems. Next, you enter this PDE coefficient according to our derived formulas. For example, you have your C formula, and C11 is D1, C22 is D2, and C12 and C21 are both 0. And C will take this row because C is the D. Okay, this is the C. And your A is your absorption coefficient. So this is your A. And also A will take sigma S. Okay. And this is your D. Okay, this is your D. Just follow this those equations. Okay. For example, A11 is sigma A1 plus sigma S12. Then A21 is negative sigma S12, and A12 is 0, and A22 is sigma A2. And for the D, do not forget to change this one, the D22 to 0. Okay, by default it's not 0, so change it to 0. Then you have the D11 is mu sigma F1, and D12 is mu sigma F2. This is for core 1, and make sure that you are taking the value for core 1 material. Then do the same thing for the core 2. Okay, do the same thing for the core 2. And pay attention that you should take the value for core 2. Another thing is that make sure you choose the eigenmode. Okay, choose eigenmode so that the C, A, and D are available for you to change. Then the reflector. Okay, reflector. And when you enter the A11, note that it is possible to enter a formula. So just enter this value plus this value and leave it in this way. And the MATLAB will automatically calculate the value, the final value. You don't have to calculate manually. Then is the boundary condition. For the vacuum boundary condition, it is Newman. And for Newman vacuum boundary condition, the G are all 0. Okay, G are all 0. Then Q11 is 0.46922, and Q22 is the same value. And the other two Q values are both 0. For the mirror boundary condition, it is also Newman, and both G and Q are all 0. And then it will be the mesh. Okay. And again, I would recommend you change the mesh parameter. Do not refine the mesh. And because that method, the refinement of the mesh will give you low quality of the meshes. And in this case, we change the maximum edge size to be 1. Okay. And also, you should change the eigenvalue search range. Reduce that one from 0 to 100 to 0 to 2 or 0 to 1. Okay. If 0 to 1 does not give you any result, then you further change it to 0 to 2. Then we will have our K. Okay. Recall that our K will take the smallest lambda. And now you have 2 energy groups. So you have the flux for group 1, that is U. You also have the flux for group 2, that is V. Okay. And also, if your neutron flux are all negative, you need to plot the negative U and also negative V. Okay. You may also plot the 3D configuration, a 3D flux distribution. Okay. So as shown to the left figure is the U. Okay, that is group 1 neutron flux for this problem, and the red figure is the group 2 flux distribution. This will conclude this lecture for 2 groups, 2-dimensional steady-state neutron diffusion equation solving in a block reactor, okay, in a simple reactor. In the next class, we are going to study how to solve the multi-assembly reactors.